So last time we did the kind of the rocket soft landing thing, right? So how to land a spaceship. Super fun. It's one of my favorite things. Um, and so today we're going to kind of continue this like little, application sort of survey kind of thing and talk about autonomous driving. So how to drive a car. And then as a like little teaser bonus thing, at the end, I'm going to talk a little bit about game theory and specifically game theoretic MPC, which is something that we've worked on a bit in the autonomous driving context specifically, which is kind of how to reason about multi-agent interactions, like how to maybe in a planner or controller, how to think about other non-cooperative, potentially adversarial agents in the environment who are maybe interacting with you and how your control actions can influence their behavior and vice versa, and how to think about that. So that's kind of, maybe we'll finish off with some of that. Okay, any questions? We'll get into it. Cool. Okay, so first, a little bit of like a history thing for autonomous driving. So this goes back really, really far, surprisingly far. In fact, like basically as far back as driving. And there were primitive demos of, kind of like things that were approaching autonomous driving going back to like the 1920s and 30s. And the way these things were done at that time was like by building road surfaces with embedded things. So like, for instance, embedding markers in the road surface of various kinds, like magnets and things like this, where the car would essentially track these markers in the road surface. And then actually beyond that, in the 50s and 60s, like post-World War II era in the US, the Department of Transportation did a series of demos of autonomous buses for cities. And the way this was done was special bus lanes. So somewhat like the bus kind of lane system in Pittsburgh, actually, where they would be in these specific lanes, and the lanes had, again, marker systems, sort of like, whatever, that were there to basically make the navigation problem easy, and these buses could drive around in like a closed circuit in a city in the 50s and 60s. So that stuff was all, I would say, like primitive, like primordial autonomous driving that isn't what we would think of as autonomous driving today. The first work that is really kind of traceable to like the modern era of autonomous driving really started in the 80s. And this is an area that's like a very big sort of proud legacy of CMU, actually. This is in many ways the birthplace of modern autonomous driving. So a lot of that work was really at CMU early on. And then also in Germany, there was quite a bit of work by Mercedes-Benz and a couple of universities. So these were kind of contemporary things. They were both happening kind of at the same time. So that happened. So let's say fun trivia kind of question. When do you think the first autonomous coast-to-coast drive across America happened? Anyone have a guess? This is a CMU trivia question, actually. You guys should know this if you're like CMU folks. Take a guess. 2005. Earlier. Yeah, so it was 1995. And it was CMU Nav Lab driving from like Pittsburgh to California in a minivan that was like basically the entire back of the minivan was just full of racks of computers, is what it took. But it had all of the stuff we would look at today. And it had camera systems, it was all machine vision, kind of all the autonomous path planning and control. Yeah. I don't think it was bad. I mean, I think it was too long for that. I genuinely don't know. I'm wondering, like if they ran a super beefy alternator to do this, but I really don't know. I don't know how much current a conventional like alternator on a car generates. That's a very good question. But yeah, presumably this was like kilowatts of power, right? It was like a server rack in the back. Yeah, like an AC unit in the window too, probably. Yeah, I really don't know these answers. This is a fun question. I mean, so this stuff is literally that lab, that nav lab, was literally cleaned out of the basement of like Ween Hall and NSH. Like I think NSH like last year, like there was like a fire sale of like 90s vintage computers and crap from this. So this stuff was like literally still here as of like this past year, like 2024. So you could go dumpster diving. And I think someone finally like retired and somebody wanted the lab space. So it finally got cleaned out. But this stuff is all still kind of has anyone gone in the basement of NSH and like the A and B levels? There's random weird like 30, 40-year-old robotics artifacts all over that basement. It is kind of fascinating. If you haven't been down there, worth a little like, dumpster dive, like perusal. There's some crazy stuff down there, including, many artifacts from the early days of autonomous driving at CMU, which is kind of cool. So, yeah, so the 90s were like a big, kind of time for this stuff where there was a lot of progress.
They documented day by day.
Oh, yeah.
I just found.
Oh, that's awesome. Yeah, yeah. So, I mean, this is very much a CMU legacy thing that like while you're here, it's worth kind of poking around and seeing some of this stuff if you're into it, because it all happened here. So there's lots of work in the 90s. And in particular, this like CMU coast to coast trip in 1995 was like, I think 98% autonomous in terms of miles across the country. So they had like a safety driver in there that had to take over once in a while if there was like bad weather or highway construction with like crazy stuff. But there were, really, so it's interesting. Okay, so this is literally 30 years ago, right? 30 years ago this year that this happened. 98% autonomous miles coast to coast across the US. Around the same time, right, there were similar things done in Germany on the Autobahn. So we're talking 30 years ago, we were at 98%. Where do you think we're at now? I don't know, but it's probably 99 point something, right? So just the fact that we've literally spent 30 years chasing 1 extra percent on that, I think is really, really telling about how much of a long tail problem this whole thing is. And like how hard I think we're going to be chasing that last percent, that last couple nines for a really long time. So it's so much weird stuff can happen, right? So let's, for fun, let's look at some of that because it's cool. So here's like, this is the van. This is like on YouTube, worth a look. That's the van in question. So 98.2% autonomous miles in like this coast to coast driving attempt. I think in here, if you go pay attention, yeah, so this is like the vision system running, right? And then this is, okay, so then this is 10 years later, this is the DARPA challenge stuff, right? Which famously CMU won this thing. And this was another huge kind of leap forward driven by like DARPA investment, and basically all the big, schools had teams in this. And the legacy of this really is that, and so this is 20 years ago now. This was happening when I was an undergrad. I was a freshman in 2005. And I remember I was at Cornell, and Cornell had a team that famously crashed with MIT's vehicle during the challenge. And so I remember like seeing this thing drive around campus when I was a freshman and like thinking it was cool. Anyway, yeah, cool stuff. But yeah, what I was gonna say about this is the legacy of this specifically, though, the DARPA challenge, is literally every autonomous driving company out there today spun out of one of these teams pretty much. So like the Stanford team that entered this became Waymo. The CMU team actually spawned multiple companies. So like this really, I think, was the kernel from which the autonomous driving scene we know today kind of emerged, right? Okay, so that's cool stuff. More YouTube videos later, but some CMU history there for you. That, and then yeah, so just like that DARPA challenge stuff was also a big deal.
John talks about the emergent and power problems they have.
Oh yeah, cool. You should send this out. Yeah, it's really fun. I don't know about this, so I'm curious about this now.
It's day by day. It's amazing.
That's awesome. So yeah, DARPA early 2000s was a huge catalyst. And everyone knows, right, Red Whitaker kind of ran that program here, and there's a whole history there too. And a lot of these guys are still around. It's worth talking to them, if you get a chance. Okay, so that's kind of a little brief history. And then like what I'd like to do now is kind of give a very, very cartoonish overview of kind of the full stack for one of these things. And this is, again, very cartoony, very high level, and also very like, I don't know, this is vaguely the standard, but there's many, many ways to like, skin a cat. Like people do this differently. There's lots of ways to do it and put the pieces together. But roughly speaking, there's a perception system, which at this point is, all machine learning driven. But these typically look like, classifier networks that are saying that's a person, that's a motorcycle, that's a traffic cone, that's a truck, that's a car, whatever. And then they put bounding boxes around these things. And then typically the output of that perception network gets fed into something classical, like typically a Kalman filter that's doing tracking on these things, that's leveraging IMU, odometry, all the other stuff on the car to kind of smooth these things out and sort of propagate them to the next time step. And there's lots of ways to fuse that stuff, but I'd say that's kind of the standard. And it's over time crept more and more towards the neural network sort of chunk growing and assuming more and more of the role in this. But I'd say, perception is mostly learning, mostly doing stuff like that, right? And then from there, the next piece is there's kind of these two different pieces. So there's typically a path planner. And then what on top of this, I would maybe call a route planner. And the route planner is basically like Google Maps, right? So that's using graph search techniques and like maps to plan a driving route from point A to point B. Think Google Maps, right? So that's kind of giving you waypoints. And then underneath this path planner, this is typically some kind of search-based, sample-based planner that's like saying, okay, over some horizon, here's all my obstacle constraints. And then I need a smooth path in like XY space, like along the road surface that is collision free. So basically, this is just giving you a collision free like XY path through space, right? And so typically there's like, kind of all the standard search-based planning algorithms you can apply to that. It's low dimensional, but the real point of it is to get you a smooth collision free path. And then typically next after that is an MPC controller, which is then taking that like just XY curve along the road surface and reasoning about the car's dynamics, throttle and steering commands, all that good stuff, and trying to track that smooth path on the actual car hardware. And then this is sending those commands to the car. And then we kind of close the loop with our sensors. And again, this is like very high level cartoony. This is more or less standard how this is put together, but there's lots of ways to do it. I think this is still more or less what most of the driving stacks look like. Modulo, like where the, learning is. I think everybody's still pretty much doing MPC kind of at the end of this whole thing. I think most people are still using like some kind of Kalman filter thing somewhere in the perception system to kind of like do a lot of outlier rejection and kind of keep things on the rails. But for sure, over time, the amount of learning has gone up and up and up as a general trend. On the sensor side of things, typically GPS, IMU, kind of always, and then cameras, and then often radar and LiDAR to varying degrees. Famously, right, Tesla doesn't like radar and LiDAR and thinks, only cameras. I would say, though, from a practical standpoint, automotive radar, because of the industry growth, is stupid cheap and quite good. So like from a practical standpoint, there's almost no reason not to use radar. You can buy dev kits from like Texas Instruments, automotive radars for like $100. And in volume, like you can buy the radars for tens of dollars, like they're cheap and they're really good. And they give you kind of very complementary data compared to what cameras can give you. They're very useful. They're also in regular non-autonomous cars for like the backup, beeping and stuff like this. And they're so cheap that there's like almost no reason. LiDAR is the costs have come down a lot because of the autonomous driving world, but LiDAR is still expensive. So I'd say like there's a good argument to be made that like eliminating LiDAR is makes sense from a cost perspective. But I would say radar is super cheap and like there's almost no reason not to put radar on these things. Yeah.
Do the radar sensors normally give you like a single flight point?
No, they're point cloud kind of things. Yeah, they give you there's like a field of view, and then they're just like it's basically a point cloud, like it's a depth sensor, right? And they typically go out to a couple hundred meters in the kind of maximum case, but it's like this kind of, cone situation where it's angular resolution. So like stuff far out is effectively much lower spatial resolution than stuff up close, but it's for basically detecting like there's a car in front of you at whatever distance, right? So it's used in like all these kind of safety intervention kind of systems, like where it'll like slam on the brakes if you're going to rear end somebody. That kind of stuff is usually driven by radar sensors.
How sophisticated is the damage not being made?
We're going to get there right now. Yeah, this is kind of what we're going to talk about today. And it's, I think, pretty interesting. And then I think a high level comment is that I would say the control part of this is not that hard. Basically, the control problem here is easy and is more or less solved. Same thing with the planning. Like all this planning control stuff, we can do this with like classical methods. It's all straightforward. We know how to do it. The perception part is the hard part of autonomous driving. And depending on how you want to like draw the lines, I'd say it's a combination of perception and reasoning about other drivers. Like these are the challenges. Perception's hard in like rain and snow and, you know, all kinds of weather conditions. And then like reasoning about what other human drivers are going to do, because people do insane stuff all the time and are irrational and dangerous in all kinds of terrible ways and hard to predict, right? So predicting what other humans are going to do, which you can call perception, but is kind of this other thing, right? Because it's also coupled into the control problem. So you need to act in such a way that you're kind of responding to what the human might do. And in general, you also need to kind of like act in such a way that you're reasoning over their potential actions and how those are cross-coupled into your actions, right? So this is actually really subtle and complicated. That's hard. Those are the hard parts. Kind of the sort of standard control stuff is pretty easy. Let's see, what else is there to say about this? So what's that?
The response times they have to respond
To what a human is doing if like someone jumps in. Yeah, I mean, there's ultimately hardware limits there. I think the control loops, like we can run these things fast enough that it's the control response time is not the limiting factor. It's the car's dynamics. Like we can run these things faster than the car's dynamics at this point. So like, you know, we can run these kind of MPC loops. I think kind of standard for most of the stuff, even like the crazy stuff, which I'll show you some of, they run those loops at like 50 hertz, and that's more than you need because the cars are not that fast. Like think about human control loops. If you think about like the visual motor loop on a human, that like your response times are worse than that actually. Like the fastest a human can respond to like some kind of visual thing. Like if you see a kid running the road and need to slam on the brakes, human response times are maybe 20 milliseconds in the limit, like as fast as you possibly can. They're worse than that, in fact, right? So like so that's 50 hertz. We're worse than the MPC at this kind of stuff. There's also been a lot of work on things like event cameras and stuff like this that are really crazy fast, and from like this kind of closing the vision loop perspective, way faster than a human. So like these kind of systems are better than a human at things like slamming on the brakes if a kid runs in the road. And again, it's really at the limits of the car's dynamics more so than the sensors or the control algorithms, I think. Okay, so route planning, this is the Google Maps problem. This is basically graph search to generate waypoints. Then we've got kind of the path planner. This is kind of, again, usually using some kind of search-based planning, could be sample-based, could be graph search, kind of technique. But the ultimate goal of this thing is to generate a smooth, i.e. like typically a spline curve that is collision-free. So this is just a geometric curve like on the road surface in 2D. No reasoning about dynamics at all. Just about sort of being collision-free. Because again, obstacle avoidance is non-convex, right? So that's why we do this. We want this thing to generate us a nice collision-free path through the random, weird, non-convex obstacle landscape. Once I have that, I can then pass that down to my MPC controller, which can then solve like a convex or convex-ish problem. It turns out that the standard is to do nonlinear MPC here with a nonlinear bicycle model for the dynamics, and just let it rip with some safeguarding and whatever. But that's kind of the standard thing. So that's kind of next. PC controller. This then basically is trying to track that spline curve while reasoning about vehicle dynamics and constraints. So in particular, you can imagine, right, if I have a collision-free path with like margin on it, I can basically like linearize my obstacle constraints around that path and get something that's convex through like a corridor, right? That's kind of a standard kind of thing. And then I might have nonlinear dynamics. They're pretty benign, though, so that's fine. And then I'll have like, steering rate and acceleration constraints from the vehicle, right, that I want to respect. So that's kind of what that problem looks like. And this is the part we're going to talk about mostly today, because it's kind of the stuff we do in the class. So they tend to not do that. And the way they get at it instead is by like basically enforcing curvature constraints on the splines. So you can kind of do it this way geometrically, such that you don't have to. And for kind of standard driving, you're not trying to push the limits of the hardware, right? You don't want to like be railing your tire friction limits and stuff if you're driving around town. So like all of this is done with like very, very conservative bounds with lots of margin, so that you're like driving the car in a very kind of benign, well within the limits kind of way, such that like this decoupling is perfectly fine. And like those issues kind of don't come up because you just put very conservative curvature constraints in the path planner, and then like you're way, way inside the steering rate and throttle limits when you're using the MPC controller, unless an emergency situation pops up, in which case you'll do whatever you've got to do, right? Slam on the brakes super aggressively, this kind of thing. Okay, any questions about this so far? So now we're going to talk about the dynamics model and like kind of what's standard for these vehicle dynamics things. So I'd say there's sort of lots of options here. There's kind of a hierarchy of standard models that people use, kind of with different levels of fidelity depending on the application. And it's kind of always one of these things, you want the model to be good enough for doing the control task that you care about. And in a lot of cases, you don't need a super high fidelity model, again, because we're not trying to hit rail the limits of the car when we're trying to drive around town in most kind of settings. So most commonly used across maybe a surprising array of situations are so-called bicycle models, or also sometimes called single track models. And there's a few variations on that theme as well. The simplest is called the kinematic bicycle model. And this is surprisingly applicable to like most standard flavored on-road driving kind of scenarios. So draw sort of a cartoon. So like we'll have kind of 2D, X, Y, and then theta coordinates. So we have the bicycle model implies we have kind of two wheels. We have a back wheel. We have a front wheel. We have some angles here. So you have like a heading angle theta. We have a length between the wheels, L. We have a steering angle alpha. I think that's kind of it. And then the inputs to this thing, again, there's different versions of this. The kinematic version, your inputs are basically the throttle or the velocity command, and then your steering angle command alpha. Or you can add an integrator to this such that you can handle acceleration and turning rate limits. So you can make it v dot and alpha dot, and just kind of put v and alpha in the state vector and have an integrator. I'd say that would be like what I would do, because you often want to be able to reason about like acceleration and turning rate limits explicitly, right? Okay, so if you assume the tires don't slip, you can do a little bit of kinematic kind of stuff, a little bit of trig, and derive some really simple equations for this. So x dot is v cos theta, y dot is v sine theta. Theta dot is a little trickier to figure out, but again, not super hard. It's v tan alpha, which is the steering angle over the wheelbase L. And then, yeah, if you want to add the integrator stuff, you might end up with like alpha dot equals you. You might do something like, for instance, v dot equals u1 and alpha dot equals u2. And then your state vector here, pardon the abusive notation, would be like xy, theta, alpha, then like v, or I guess I might want to flip that around. Alpha, and then your u would be v dot alpha dot. Cool. Okay, so this is like very, very standard. And I would say kind of works well for sort of quote normal driving on the road, et cetera. Where again, you're not pushing vehicle limits. You're not gonna like, squeal the tires, like slip it all. You're not like pushing the acceleration or cornering limits of the car at all, right? But this will break down in kind of any of those kind of more aggressive settings. So anytime you're pushing the cornering limits, possibly slipping the tires, situations maybe where body roll becomes important, that's not accounted for, right? So all these things can cause trouble for this model. So in, let's say, more aggressive settings, which basically comes down to high acceleration. Okay, so from here, there's like lots of places to go, but kind of the next place to go up in the hierarchy of like more complex models that people use. The first one is the so-called dynamic bicycle model. This one essentially models the car still with only two wheels, but it models it as like a rigid body, and then kind of adds up forces and torques, and so can reason about torque, tire forces, braking, like in a more kind of rigorous way. And this already gets you quite far. In fact, I would say for on-road driving, this is probably going to cover just about everything you would ever practically care about. So F equals ma, kind of torque stuff. This can reason about engine torque pretty explicitly, tire forces, braking, kind of all these kind of force things, right? Explicitly in the model. And this is good for like more dynamic behaviors, right? Let's see. So after that, if you're going like, really aggressive, like maybe racing scenarios, drifting scenarios, although I'll show you some stuff. And then maybe getting into like off-road scenarios where the loading on the different sides of the vehicle become important, and body roll dynamics become important. This is where you might go to a so-called double track model. And that's basically the full car dynamics now. So you have now all four tires, full 3D rigid body dynamics. So now you can like reason about the suspension in particular, right? In most cases, you don't need to. So this can like now reason about body roll, kind of weight transfer between the tires. So this is like aggressive cornering scenarios, racing, drifting, and like maybe off-road driving. Okay, so that's basically, yeah. I think there can be, but I'd say in these scenarios, if you have a high fidelity kind of model like this, and you're reasoning about the suspension, for instance, and all this, I don't think it shows up in that kind of context. Like the static indeterminacy thing you're talking about is like the table, right? The four-legged table kind of scenario. That specifically happens under strict rigid body assumptions when there's no deformation. And here you're kind of not doing that because, for instance, if you're gonna do this double track thing, the reason to do it is to reason about, like, for instance, the suspension dynamics and things like this. So as soon as you put in like deformation in the form of like springs and dampers in the suspension and like complicated tire stuff, this kind of static indeterminacy stuff goes away, basically. For instance, if you take the table example, actually, and you stick springs in the legs of the table and make them prismatic joints, it goes away. So that thing is a particular quirk of the rigid body assumption for like specifically for like, a rigid, say, four-legged table or something. It's a corner case that is almost like unrealistic in some sense, right? Because like as soon as you add any kind of deformation, any kind of compliance, it goes away. So this would be a scenario where I don't think you would run into that, specifically because the reason you would do this is to model some of that compliance in like the suspension, for instance. And then kind of building on that theme a bit, the really hard part of all this stuff, like this is all well understood stuff, right? Like rigid body dynamics, whatever. The tricky part for this kind of thing are really the tire dynamics. And there's like a whole range of tire models, but specifically tire friction with the ground is like super gnarly and hard to model if you try to push the limits, if you're trying to push the limits of your grip and cornering. So like if you're doing simple around town on the road stuff, it's easy and you don't have to worry about it. And you can actually often make no slip assumptions. But if you start to do anything aggressive, it can get pretty serious. So for instance, you can go from like super simple, which would be around town driving, no slip. The next version to sort of medium complexity would be like a Coulomb friction model, which is a stick slip model where you have a friction limit. Like that's kind of pretty standard once you start going to, push these limits, to like super complicated, which in the tire world, they're like super gnarly, highly nonlinear models that include like contact patch stuff, deformation in the tires, nonlinear friction, all this kind of stuff. There's a famous, the Pacheco model, if anyone's heard of this, is a famous, like widely used gnarly nonlinear tire model, sometimes called the magic tire model or the magic formula. So that is like, kind of one of the standard things that's in this complex realm. So these things can think about, contact patch, deformation in the tire, and then like nonlinear friction stuff, all kinds of weird, gnarly stuff if you need that, right? Okay, so this is kind of, yeah.
Even like the most complex tire models, like how do they like address things like sand, for example, like deep sand?
Yeah.
More fluid into
That's super gnarly. So this gets into, so like this, what we're talking about here is still pretty much on road and maybe like benign off road. If you're talking about like situations like super loose terrain, sand in particular, now you're in the realm of what people call terra mechanics, which is like how things interact with things like sand and loose soil and stuff. This is a really gnarly field. And there's a lot of work on it, particularly people in off-road the people that actually maybe care the most about this, there's biomechanics people who study locomotion in these kind of contexts. And then there's also the people who I think spend the most time thinking about this for tires and wheels are actually the planetary exploration folks who like do Mars rover stuff. They do an insane amount of modeling and like experimentation to figure out like exactly how weird wheels and tires will interact with like Martian regolith, for instance. And there's a whole rig set up in the high bay here, that like down below us actually, that's like for exactly this purpose for lunar rover kind of applications, right? So yeah, I think a lot of that work is empirical. Like there are in semi-empirical models of this stuff. You can simulate it, but it's super expensive. Like these kind of granular media things are in this really weird, annoying place where they're almost a continuum. Like they're sort of halfway between a really, really high degree of freedom, like multi-rigid body thing and a fluid, like continuum thing, right? And they're in like the worst of both worlds in some sense, right? Because they can exhibit jamming effects that are very much a rigid body thing, where you actually have to simulate all the grains to capture. But then sometimes they flow like a fluid and you want to model them like a continuum, and they're just annoying and terrible to model, frankly. So there are simulators for this stuff. There are semi-empirical models that are from, fit from data. There's all kinds of stuff. I think if you really care, you end up in like a more experimental data-driven mode. There is for specifically for off-road autonomous driving, I think people have more or less gone down the path of just data-driven models of these things. So you drive a bunch, collect a bunch of data, and try to like ultimately like learn some kind of predictive model for what's going to happen. Okay, yeah.
Do any autonomous cars use any of these models besides the simple ones in like the emergency scenarios? Or like if they had to predict how slamming on the brakes?
Yeah, that's a really good question. So to be honest, I'm not 100% sure. Let me show you some stuff. So these guys at Stanford, you guys have probably seen some of this at this point. This is Chris Gerde's group at Stanford, who's done, the first one I'll show you is autonomous drifting. So these guys, like, excuse for doing this work is safety scenarios, like evasive maneuvers where you have to reason about these kind of effects. So they pitch the work specifically for that. And that's how they get funding. They're like, oh, we need to be able to reason about these kind of things because in an emergency scenario, you might have to, you have to drift your car around the child in the road or something. So that's actually their pitch for this, is exactly those scenarios. So I don't know how much of this is actually deployed in cars. I will tell you that, like, Toyota Research, for instance, funds this kind of stuff, and they definitely sort of, use some of these things internally. Whether they're doing this, sort of stuff in the emergency, sort of stuff in their control stacks on the real deployed cars, I would be a little surprised if they were, but that's the stated goal of a lot of this work. So the reason I want to show you this is awesome, obviously. This is actually using a dynamic bicycle model. It's not even a double track model. It's a dynamic bicycle model, a single track model with a good tire model. So this is using like a sophisticated tire model to handle all that stick slip stuff, like Pacheco model. I'm not entirely sure actually, but that's what it is. It's not actually a crazy sophisticated dynamics model. I think the performance here, the stuff that I find super impressive, is their model of like the tire stick slip behavior is good enough for them to do really precise handling here. If you pay attention, they're driving between hay bales with only a couple feet of clearance. So it's really, really accurate. Like, it's surprisingly, that's the part that's surprising to me. So super cool. Watch the YouTube videos. It's also awesome that it's a DeLorean, because Back to the Future.
Temperature estimation, right? Because like that's not
Really. So yeah, 100% does. And this is a whole other thing to get into. But I know. So here's, if you guys want to know what they're doing exactly, here's the paper. You can go read the paper, and if you kind of dig in, it's a single track dynamic bicycle model. All the stuff's in here, and the tire model stuff's in here as well. And it's nothing crazy. It's like a pretty straightforward tire model, and like literally just vanilla MPC. Like, they basically set this up and do nonlinear MPC on this thing. And then maybe one more for fun. This is them doing autonomous racing on their other car, which is an Audi TT. Just for fun, we'll throw this up here, but same story. It's again, dynamic bicycle model, single track model, good tire model, and then like nonlinear MPC. Literally, they're doing co-location with IP opt on the car at 50 hertz. So it's literally the stuff we did in class. Like, you could read the paper and code this up. It's exactly the stuff you've done. There's no secrets. I know this because I was on a couple of these guys' PhD committees when I was at Stanford. So I know kind of exactly what they did. I read the dissertations, and that's it. And so similarly, there's papers here. Got the paper you can check out. I'll post the stuff. But again, like, that's what it is. And these guys are at the level where they beat pretty much any amateur race car driver. And they're sort of just shy of the like performance of a professional Formula One driver. They still lose to Formula One drivers. One of the interesting nuggets there is just how fast those guys are and what decides. They're literally 1/10 of a second is a lot for a lap time for a pro F1 driver. So that's the level those guys are at. It's kind of wild. So they're basically almost at that level. I think they're a couple tenths behind what a pro F1 driver can do on the same course with the same car. And they've done experiments. So question is, right, these guys are doing nonlinear MPC with this model, blah, blah, blah. And they're doing the optimal stuff, right? They're basically solving that optimal control problem online. They're railing all the limits of the car in the controller, like going right at the limit. Why does the F1 driver still win? Like, what's the missing piece?
Yeah, probably learn it better, but probably brain to like understand how to push it actually a little bit better.
Not really. So like, that's kind of not what it is. It's so I'll, yeah, other thoughts. No, they're using GPS. They've got like, centimeter accurate. Yeah, so that's kind of getting at it. Yeah, it's the tire modeling. Yeah, who else had thoughts? Yes, so this is kind of really getting at it. So, okay, so the dynamics models are really good. It's the tire model. So here's the really wild thing. So again, I saw this in some dissertations. So they compared data for what this controller does versus what the F1 driver does. And there's one thing that stands out a ton, and it's basically that. So the deal here is the tire friction varies with temperature, varies over the track, right? It varies lap to lap as you heat up the tires, all this kind of good stuff. So the friction coefficient's varying. And the optimal thing to do, right, is to go right up to the limit of your sticking friction and not cross it. Because if you cross it, you lose friction, right? You start to slip, and that's less cornering ability. So the optimal thing is to go right up to the limit of your friction cone. What the MPC controller has in there is it's a model of tire, nominal model, has a friction cone, whatever. It goes right to the edge and doesn't cross it because that's suboptimal to cross it. So it never slips. If you watch the F1 driver, they slip constantly all the time in little amounts all over the track. And if you interview them and talk to them about what they do, they feel the slip and they listen for tire squeal. And they are constantly pushing the car just past the friction limit, because in order to measure the friction coefficient, you actually have to exceed the limit, right? So to do this, so basically what the Formula One driver is doing is constant online system ID/adaptation. And they're actually building over the course of the track, they build a mental map of the friction coefficient over the entire track. They learn where there's more grip and where there's less grip around the track, and they're dynamically updating that map as they drive. So that's like, I think the big missing link is that the human drivers are doing this kind of exploration where they're, again, doing something that in the nominal case is suboptimal by slipping, but they're using this to update this estimate, and they're tracking this lap to lap, and they're then able to like go, again, closer to the limit than the controller can, because the controller is not dynamically updating that friction estimate. So that seems to be the missing link. And I think that's super cool. So presumably you could do that, right? So if you want to check some of this out, here's the paper that goes along with that video where they talk about the autonomous driving setup. Again, it's literally IP opt co-location, 50 hertz with like a nice, dynamic bicycle model with some tire stuff. Pretty straightforward.
Why is slipping exactly suboptimal?
So slipping means so the way friction works, your static friction is your highest friction. When you slip, you have less friction. The friction force drops. So if you try to corner as fast as possible, you want to use as much friction force as possible. So if you slip, you're giving up cornering ability, and you're actually slower if you're slipping or drifting through the corners than if you were sticking. Because what they're doing is slipping little bits all the time to estimate a more accurate, sort of spatially and time varying estimate of where the friction limit is. So it's an exploration exploitation thing. So they're doing the exploration to learn where the limit is dynamically and keep updating it in little bits all the time. And then knowing that, they can push harder because they know where the slip limit is better, right, than this controller does. Yeah. Yeah, that would not surprise me at all. That's a reasonable thing to do. Like, people definitely have done various flavors of this. Like at a baseline level, you can take like the Pacheco model and just do parameter estimation through that. But yeah, you can do all kinds of, data-driven approaches to like learning better friction models. That would, like, if you wanted to make this, if you wanted to kind of, try to beat the human F1 driver, that seems to be where the missing gap is getting that friction knowledge improved, and specifically doing online adaptation and kind of like knowing where it varies over the track and knowing how it's changing temporally based on temperature, et cetera, seems to be where the missing link is.
Is one way to do that, like, make your friction cone a little bit bigger, as like loosen the constraints slightly to allow it to slip, and then have it?
It's a little subtle, right? So it's a non-smooth, non-linear phenomenon, right? So you don't actually know where the limit is till you cross it. So you have to slip in order to detect where the limit is. And so to do that, you actually need a controller that's got some kind of information seeking objective. So you actually want to trade off. This is the classic, exploration exploitation trade-off in POM-DPs that we kind of touched on. You basically have to have the controller reason about what the uncertainty is, and then make specific control moves that are tailored to teasing out information. Because doing that slipping is suboptimal with respect to lap time, right? But in order to get that to fall out, you need to have the controller explicitly reason about, well, I don't know quite where the limit is. So if I do this experiment and slip a little right now, that's going to give me information that I can use to get faster later, right? So it's giving up some time now to potentially have some wins later on. And so that's a complicated thing that naturally falls out of dynamic programming, stochastic dynamic programming and various things, but like does not naturally fall out of like a sort of more vanilla MPC framework like this.
Also because the F1 drivers know how much to slip without losing control because they've learned that really well.
Yeah. I mean, it's all very subtle and complicated, but yeah, the takeaway I got from this was how wildly dialed in those F1 drivers are and how much skill is involved. It's insane how good those guys are. And like the difference between like being a tenth of a second slower on a lap is a huge amount for those guys. And like the level to which they've dialed this all in is wild. Like it's using auditory cues, like all kinds of other sort of sensory cues that they're doing all kinds of really kind of next level stuff in ways that are pretty impressive. Okay, so that's fun. Takeaway there is though that like for kind of on-road driving, I would say that's kind of state of the art circa a couple of years ago. And they're using single track, dynamic bicycle models. So I think the implication there is you don't necessarily need the double track model, and it maybe buys you very specific things. By the way, if you wanted to really beat the human and cheat a little bit, one thing you could do with this MPC controller that would flat out let you beat the human is force vectoring to all four tires. So like the human only has access to one gas pedal and one brake pedal, but modern cars, especially modern all-wheel drive cars, can actually do vectoring to all four tires. So they can apply different force to all four tires. And if you just threw that in the controller and gave it the ability to do that, I think almost out of the gate, you'd be able to beat the human just from that additional control capability. So,
do that like in F1, because now that you're saying that, it feels like it would be an advantage for people. If they have
100%. But I don't know how you would do that with a human driver, right? Because you don't have enough limbs to like do all that. I think it'd be kind of wild. But yeah, in principle, this is a win. And like you could do it with the autonomous stack in ways that like humans just can't do it, right? Yeah.
Basically,
Yeah, so that stuff like ABS brakes do this, right? Traction control systems do this. But they're doing it from this perspective of not wanting to slip and wanting to stay safe. If you sort of if you put those control knobs at the disposal of an MPC controller that's trying to minimize lap time, it would be able to take advantage of that stuff and reason about like body roll and loading of the different tires differently to really go. Basically, what you get in a double track model is you get a different friction cone per tire based on the body roll dynamics. So like if you're leaning into a turn, there's more friction available on like one side of the car than the other. So you can exploit that with your braking and throttle commands to get even more, right? So that's kind of like where you could go with this, where I think, like without having to go as crazy on the like, exploration, end of things, you could probably get a win with that kind of already. Okay, so just some dynamic bicycle model. This is what that stuff I just showed you is doing with good tire models. Gets you really far, basically. And this is kind of the stuff I just showed you. If you read the papers, this is basically doing online nonlinear MPC with IP opt running on the car at about 50 hertz. And that's kind of all you need. Okay. Sweet. So that's like basically, I would say, state of the art for on-road driving. And I think like kind of where you go from there and what a lot of people are working on now is off-road autonomous driving is obviously a really big deal. Probably some of you guys work on this stuff in here. And the big difference there, I think, is the fact that the dynamics get a lot gnarlier when you start talking about driving on sand, loose terrain, rougher terrain. Those tire sort of interactions get a lot more complicated to reason about. And then also you end up with a new flavor of perception problem where rather than reasoning about like lane keeping and other cars, you're now thinking about, can I run over that bush or do I have to drive around it? That kind of stuff, right? And so this becomes, it's actually, I would say pretty much back to the same story of the perception problem is the hard problem. The control problem is really not that hard. State of the art for off-road autonomous driving is basically doing MPPI, which is another thing that I threatened to maybe talk about. Who wants to hear about MPPI versus behavior cloning next time? That's another good topic we could do. Show of hands. Who wants MPPI, stochastic MPC stuff? Who wants behavior cloning stuff? It's like kind of half-half. I think slightly biased towards MPPI. So maybe we'll do that. I'll do one more. Maybe I'll do a Piazza poll. But yeah, those are both good topics that we could talk about. Anyway, so for off-road autonomous stuff, basically everyone just throws MPPI at it with like a learned dynamics model. By the way, the real reason they use MPPI there is because ReLU networks are not nicely differentiable, and gradient-based optimization, like more vanilla SQP type MPC with IPOpt or whatever, doesn't play nice with neural network dynamics models. Whereas MPPI just does random sampling and rollouts and doesn't care. So that's, I think, the real reason that's popular in that space. So learned dynamics models often like learn perceptual models, right? That are also sort of like telling you if a bush is safe to drive over or not with like kind of traversability maps, this kind of stuff. And you just run MPPI over the whole thing, which is just MPC, right? Okay, cool. So that's that. Any other questions, thoughts about MPC for driving? On-road, off-road, et cetera. Okay, cool. So with the remaining time, I wanted to like tease some maybe a little more out there stuff, and sort of a different viewpoint on some things that maybe is something that's less standard. So who's heard of the frozen robot problem? Anyone? Could you describe it?
If the other robot's gonna go to the space that the other robot wants to go to.
Yeah, it's sort of this deadlock situation that can arise in collision avoidance scenarios, right? So it happens in all kinds of situations. Specifically in driving, the classic example is highway merging. So if you're merging onto the highway on an on-ramp and there's dense traffic. So imagine it's like bumper to bumper traffic and you're coming down the on-ramp, you need to merge in. What typically happens or would happen circa a couple of years ago, and maybe this has gotten better now. I haven't tried it on my Tesla recently because I don't trust my Tesla in bumper to bumper traffic. But what was kind of standard and where this kind of came up is you would basically see this bumper to bumper traffic. The autonomous driving stack would like get to the bottom of the on-ramp and say, there's no collision-free space for me to merge into traffic here. I just slam on the brakes and sit there forever at the bottom of the on-ramp and never merge and do anything. And so ultimately, if you think about what we do in that situation, you're fundamentally solving a game theoretic planning problem where you're reasoning about the other drivers and saying, hey, those guys don't want to hit me as much as I don't want to hit them. So if I'm slightly aggressive and kind of nose my way in between two cars, they're going to make space for me because they don't want to hit me either. And mostly people are going to be cool about this and they're going to let me in. But fundamentally, what you're doing there is predicting the other agent's reaction to your control actions, right? It's fundamentally this kind of cross-coupled reasoning about what they're going to do. You have some prior over their dynamics and their whatever, their control policy, and you're thinking, if I do this, they have some collision avoidance behavior. They're going to have to back off and make some space, that kind of thing, right? And that kind of multi-agent game theoretic reasoning is not baked into most autonomous driving stacks in a coherent way. And so therefore you get some of these behaviors where the car is unable to reason about what the human might do in this kind of way, and therefore you get stuck, right? So to summarize, we want the MPC controller. And I'd say this is a particular area that's a little fuzzy, and I think a lot of the autonomous driving people are currently thinking about this as part of the perception stack, and they're kind of like doing this kind of weird learned human driver prediction models solely in this kind of like open loop prediction kind of way, where they're thinking about it again as part of like the perception system rather than kind of integrated into the control stack in a closed loop way. But I don't know, it's an active area of research. So we want to reason about coupled behavior. With other drivers. Specifically weird, crazy humans that do weird things. And basically so this is, I would say, current systems make lots of assumptions in this regard. The most basic stuff that was, maybe 5-10 years ago, I think this has all gotten better now. But a lot of kind of the classic move, say even just 5 years ago, where like the Tesla autopilot stuff was really good on the highway, but really bad in urban settings. The reason the highway driving is much better, like one of the reasons is that earlier on in the autopilot stuff, and I think similar for other auto manufacturers, like one of the key assumptions was that over the planning horizon for the MPC controller, which is only a couple seconds, maybe a few seconds, they would assume that all the other nearby cars were going to continue at constant velocity. So basically, you've got in your MPC controller, you're reasoning about your nearest neighbor cars right around you. And you're saying like over the next 5 seconds or whatever my MPC horizon is, they're just going to stay driving at constant velocity, doing exactly what they're currently doing. And that's how I'm going to reason about collision avoidance kind of planning kind of stuff. And obviously that breaks down it's a pretty good assumption on the highway and it works really well on the highway, but in urban settings, it breaks all the time and is a bad assumption, right? So, that's kind of sort of most of these simplifying assumptions work well for highway driving and not so well for urban driving. So kind of scenarios with like tighter coupling, let's say. Between cars. So this kind of like classic ramp merging scenario that I mentioned. Okay, so one way to get at this, I think the way most of the companies are getting at this is just build giant like data-driven pipelines that are kind of coupled in with the perception system. So you basically have this perception network that's trained on lots of data that is not just identifying, say, bounding boxes around kid, motorcycle, whatever, but also in addition to that, predicting, say, the next 5 or 10 seconds of the motion of these things, given some like recent history of observation. So they're kind of, this perception network is growing into this like predictive thing as well. But another way to kind of think about this, and I think that the most kind of principled kind of control theoretic framework for reasoning about these kind of multi-agent, non-cooperative interactions is game theory. And so we've done a little work on this. So I'll kind of highlight what this looks like. So we're going to talk about game theoretic trajectory optimization, or whatever you want to, like MPC, and how to kind of think about one of these things. So the high level idea behind game theory in general, and in this kind of control context, is that you're basically going to assume that all the other drivers are also solving an optimal control problem, just like me. So you're assuming that everyone's basically solving a similar optimal control problem to you, and they have similar collision avoidance constraints, similar objectives, right? So that's the high level kind of point number one. So, and then what you basically do is you make some assumptions about what their optimal control problem is. So you basically model it like they have their own MPC problem with some objective and some constraints. And you might do this for all your nearest neighbor cars. And then you write down the first order optimality conditions for their NPC problem, which is going to be in general cross-coupled to your problem via the collision constraints and everyone else's problems. And you basically stack the KKT conditions up for all those cars and solve everybody's optimal control problem together simultaneously. You solve these, ends up being a bunch of cross-coupled NPC problems for several drivers. You just are basically solving simultaneously with your NPC problem, your assumed version of their NPC problem. And what that lets you do is reason about their behavior and how it can be influenced by your control moves, right? Does that make sense? So basically, yeah, let's write some math down at a high level, but that's kind of the key idea. So you solve a joint optimization problem. For all cars simultaneously. Okay, so I'll write some of this at a high level in math. So one version of this idea that I just described, so this is a game theoretic equilibrium, is what this is called, when you basically jointly solve a whole bunch of coupled optimal control problems. It's called it's not really a minimum anymore. It's instead this weird cross-coupled joint. It's called an equilibrium, right, between multiple players. And there's multiple versions of game theoretic equilibria. The one we're going to talk about is called a Nash equilibrium. If anyone remembers the movie A Beautiful Mind, that guy. These ideas originally come from economics for how agents are going to interact in an economy, but they're broadly applicable. And what this so let's write down some math, and then I'll describe what how this all works. So we're going to define, basically what we're going to do is just stack all the cars together. So it's me and my neighbors, and we'll first stack up all the states into a giant state vector we'll call x bar. And so this is going to have x1, x2, ... to xn for n players. And then similarly, we'll stack up all the controls for everybody, U1, U2, ... to UN for n players. So states and inputs. Stacked up for everybody. And then we're going to end up with a whole bunch of optimal control problems, one for each player, that look like the following. So we're going to minimize over X bar, so the full state of everybody, and then UI for player I. And we're going to have a cost function, JI for player I, that depends on the full state X bar, and then just the controls for player I. And then we're going to have constraints. So we'll have basically dynamics constraints. And these are dynamics constraints for everybody. So that's X bar, U bar. And then we'll have, say, collision avoidance constraints, again, for everybody. So X bar, U bar. So these are equalities and inequalities, right? Okay, so this is the cost for player I. And then these are sort of dynamics and collision constraints for all cars. Okay, so we're going to get this problem that I just wrote down, right? It's basically player I, and then sort of collisions, whatever, dynamics for everybody. And we're going to get one of these problems for each player, for each car, right? So we're going to get n of these optimization problems. Yeah, I mean, always, right? I'm assuming, so I kind of have a model for me. Models are never right? They're always assumptions or whatever. So in this case, yeah, you're basically going to assume, I mean, not only are the dynamics and the collision constraints assumptions, the whole structure of this is an assumption, right? This might be a human driver who's not solving an optimal control problem like this, right? So this is a model for the world, right? It's not the whole thing's kind of lots of assumptions, right? So we get n of these, i.e. number of cars. Of these problems that we want to ultimately solve simultaneously. And so the kind of the way this is typically interpreted or stated is that no one player can unilaterally improve their cost. That's kind of the definition of in words of a Nash equilibrium. So it's like everybody's trying to do the best they can. Everyone's minimizing their own cost with their own control actions, simultaneously kind of in this joint setup. And a Nash equilibrium happens when nobody can make their cost any better unilaterally on their own, right? So this shows that this is prisoner's dilemma, right? One way of thinking about this is it's like a stalemate between all the players, right? And so this is sort of a good model of non-cooperative behavior. So if everyone's friends and everyone's got cross communication and trying to be nice, you can do better than this, like in some global sense. But this is like, if you're not cooperative agents and you're just doing your thing out in the world, this is, a reasonable model. And in the driving, on their own. So like I'm an agent in this world. If I solve this joint problem where everyone's trying to do the best they can, everyone's trying to minimize this thing, I'm going to get to this Nash equilibrium, which is I as an individual can't do any better with my own actions. And everyone is going to reach the same kind of like stalemate situation where they can't do any better just, with their own actions, right? Let's see. And then, kind of in the driving context, the cost functions here can capture driver behavior, like aggressiveness, etc. So every driver might have their own cost function, right? And we tried kind of like estimating these out online in adaptive ways, and it's kind of fun. So we had a paper a couple of years ago called Algames that I'll briefly tell you about. That was kind of the first kind of real-time capable kind of NPC flavored solver that could solve these kind of Nash equilibrium problems. This is called a generalized Nash equilibrium. The generalized part refers to the equality and inequality constraints that show up here. So the idea is we're going to write down, basically, we're going to take this problem, we're going to take the constraints and handle them with an augmented Lagrangian method, which we kind of briefly touched on earlier in the course. Essentially what it's doing is similar to like other things we talked about. It's kind of baking the constraints into the objective function with like penalty terms. And then we so that's the first thing. For each player's first order necessary conditions. So this is like, I take the gradient and set it equal to 0 for every single player. And so you're going to get this like, I guess I can sort of write it down. So we'll get like this kind of function that looks like, it's got a x bar, u bar. It's got some Lagrange multipliers for the equalities and inequalities. So we'll call those lambda. So this would be for each player. So there's an I on here. And this is going to have player I's cost. And then these kind of like penalty terms. So you'll have like a quadratic penalty on the violations, basically for both the sort of dynamic stuff here. And then a Lagrange multiplier term. And then similarly for the inequalities, you've got kind of same kind of thing where we've got, in this case, it's the positive part that only the violations get penalties applied. And then similarly, Lagrange multiplier. So this is kind of standard augmented Lagrangian stuff. So I write this down. This is basically just a way of handling the constraints in one big function. And then I just set the gradient of this thing equal to 0. So I've got grad with respect to UI, right, just for player I, of this thing has to equal 0. And then I just stack these for all the players. stack the first order necessary conditions. That gradient equals 0 stuff. And I end up with a big stacked kind of setup of like grad of Li. So this would be player 1 gradient with respect to controls for player 1 of that player 1 Lagrangian. Same deal for player 2 all the way down to player n. So I stack all those up, and those all have to be satisfied jointly, right? And then I set all this equal to 0, and then I basically solve this whole stacked set of first order necessary conditions with Newton's method. And by being clever about how you do the Newton stuff, i.e. exploiting all the problem sparsity and trying to make this go fast, we're able to run this at like sort of 30 to 50 hertz in kind of at real-time rates. I'll show you just like some toy examples of this. So this kind of solves those frozen robot problems and gets you these kind of nice emerging lane change behaviors.
High level of interaction between.
Also, we kind of looked at, yeah, so here's that kind of like merging behavior. These are like less, I think there's some in here that are a little more dense. It's like you have pedestrian crossing, you know, kind of weird examples.
Dynamic games solved.
But yeah, I think takeaway is you can actually solve these at like real-time rates.
In addition to this,
And it actually works reasonably well. Like this is non-convex, but it works about as well as doing like kind of non-linear, non-convex MPC on a bicycle model normally, but it's just a bigger problem.
Which executes our game.
And then we had some follow-up work on this where we tried to reason about the uncertainty and the assumptions about other players' costs and like estimate their cost parameters online dynamically, all kinds of fun stuff. But yeah, I don't know. This is kind of, yeah, showing you the frozen robot thing where they get to the bottom of the ramp, decide they can't merge, sit there and wait for everybody to go by. Whereas with the game theoretic stuff, it generates like kind of this more natural human-like merging behavior. Okay, cool.